Um, so yeah, sorry this lesson's a bit crazy. As I said, I didn't think the internet would be as bad as it was. Yeah. So engineering maths. Let's talk a little bit, now I've talked a bit about myself, let's talk a little bit about the history of the subject. So about, what was it, about 3 or 4 years ago, there was a question that was raised with all the teachers of maths. The question was, there were a bunch of science electives. You had advanced science, you had forensic science, and there were lots of different electives, but there weren't any electives that were relating to maths. So one teacher, hold a sec. One teacher came to the rest of us teachers and said, well, would you like to do an elective for maths? And if so, what would the elective be? And so all the maths teachers got together and we had a bit of a think to see, well, what kind of topic do we think would be a good topic to be as a elective subject? And what we thought was, why don't we call it engineering maths? Now, the reason we did engineering maths is because at the time we had a lot of year 10, 11 students, when they were asked, what do you want to do next year? What do you want to do when you finish high school? They said, oh, I want to go and I want to be an engineer. And they said, I want to be an engineer. And they said, okay. And they said, well, the problem was that they said, well, what type of engineering? And they go, oh, I don't know. I said, well, what do you mean you don't know? And it's like, well, I just thought you could just be an engineer. A lot of the students at that time didn't realize that there were different types of engineering. A lot of students didn't really even know what an engineer was. They just knew that an engineer was a good job to have. And so what we thought is, let's take this chance to make a maths elective and let's call it engineering maths. And so that's what this course sort of became. And when I was asked, they were trying to find people that would to do it. I said that I would do it. And at the very start, it was very, like, there wasn't much there was engineering in it, but there wasn't too much. What I've tried to do is I've tried to do two sort of things with this subject in my time of teaching the subject. I really wanted to add in a engineering project, like a building project, a project where students were forced to design something, work through problems, that kind of thing, and just to get you guys familiar with what it was that is, what engineering was. The other part of it is going to be a fair bit of time spent working on the physics of engineering. So when we talk about physics of engineering and maths of engineering, we're going to be dealing with all of the problem solving numbers that we need to deal with. In many ways as well, this subject, I'm going to warn you guys, is not only a preparation for physics at year 11, it's also preparation for if you decide to do methods as well. So if you're in an advanced maths, this should give you a chance to maybe get some extra pointers before you get into that. And yeah, for some of you guys that are just interested and like and enjoy playing around with your maths, this should hopefully give you a chance to play around with it and improve on it and work through some numbers and problems here. I should point out with this subject that I don't expect, it's a difficult topic. There's a lot of maths in it and it can get challenging. And ultimately, yeah, I do kind of need you guys to be pretty good, at least decent at maths. But if you're sitting there and you're thinking, wow, I'm really, really bad at maths, I'm going to struggle, I'm probably going to fail this subject, for me, all you need to do, just like in most other subjects, is give it a try. I'm going to be giving you guys worksheets to work on during this time in lockdown and isolation. And all I want you guys to do is give them a try. If you can't do them, that's okay. I don't expect you guys to be amazing and do everything. But if I see students that don't give anything a try, then I'm just going to fail those students. All right, so let's go. Engineering maths. Lesson 1. By the way, introduction. What is expected of me during the semester? Now, this is going to be a bit of a weird introductory lesson. So we're going to see how we go. Just for the record, those of you that aren't familiar with this is how I set up lessons. What I'm usually going to ask you guys to do, and not going to get you guys to do this part today. Maybe I will get you a bit later. But later on in your workbooks, and I'm going to be looking at your workbooks when we eventually do come back to in-person teaching, is what we would normally do is you write down lesson 1 introduction. This here is going to be your lesson title, and this should normally go at the top of the page. Underneath that, there is this. This is our learning intention or learning goal. And the point of this, yeah, if you can, Everest, you've just asked if you can write this down. If you want to, I would like you to write this down. A lot of today's lesson is just going to be looking at what I'm doing, but if you want to add that to today's lesson, you can. If you want to take notes during the lesson, just so you know what's going on, then that's a good idea too. So the main goal of today is what is expected of me during the semester. So the main goal is you will know what is expected of you during the semester. The other thing that I'm going to do is every lesson I'm going to have a engineer fact. And that is, you don't write this down, okay? Because obviously there's a lot of text here. Today's engineer fact is about Sergey Brin, and he was Russian, born in Soviet Russia. He immigrated to America at a very young age. He's an engineer that we're going to be looking at. He studied mathematics and computer science and became a software engineer. So software engineering is a type of engineering. We're going to talk about that. With his two friends, Larry Page, and with these two friends, Larry Page was the two created a ranking algorithm that would eventually become the backbone of that would eventually become the backbone of, yeah, system sounds are on, don't ask why. Become the backbone of Google. Google's a multi-billion-dollar company that attempts to organize all the human knowledge, and yeah, it actually does a pretty good job of doing that, which is kind of scary sometimes. But yeah, that's what this is. One of the gentlemen that came to make Google. So, and I would think, as engineers go, he is probably one of the greatest engineers that I could think of, because ultimately I use Google every single day, and I'm sure most of you guys did too. So let's start with our introduction. What is the expectations, and what are we talking about when we talk about engineering maths? Normally I get you guys to do this on paper, but because we haven't got paper with us, let's try and do this now. Could I get you guys to either, let me just, what I'm going to do is, let me do this. I'm going to create a new page like this. And I want you guys to tell me, either in chat or in person, one thing that you know that is related to engineering. I'm going to warn you guys, because if this always catches people off guard, I'm going to unmute you all in about 2 seconds, all right? So if you're listening to some weird stuff, yeah, if you're not paying attention, this is your chance to quickly, quick. Yeah, so how do I unmute you? Give me a sec, because you guys should be. Oh, I can't unmute everyone. Ah, that's a new feature. That's cool. All right, never mind then. Cool. Could I get you then instead, because I can't actually unmute you, because I can't control you as much as I can mute everyone, but I can't unmute everyone. What do you know? Could I get you guys too in the chat or anywhere else? Could I get you guys to write down something, anything that you want? Yeah, I know. I figured you guys muted yourselves. That's fine. Could I get you guys to in chat tell me something that you know that is related to engineering? We're going to make ourselves a bit of a mind map on what we think engineering is and what it can include. And I want you guys just to tell me what you guys know. I know that you guys have access to Google at your fingertips because you're doing it on a laptop, but I just want to know what you guys know. Okay, we've got solving. We've got a machine. We've got machine. Something else. Coding. Thank you, Everest. Who can give me something else that we can add on here? Improve life. That's what someone said. Electronics, physics. I'm going to put physics here. Design, I like that. Who said design? Who's that smart cookie? Jake, cool. Thanks, Jake. Force, yep. Now force, I'm going to draw off physics because, yeah, it's a type of way to talk about that. Ryan said electronics. Okay, who hasn't said something? Delina, you're here. And Arn, can you guys give me something that I can put on this list? Something about physics. And Evan, do you want to give me something if you have already? STEM? Yeah, I think so. Oh, Najila's here. Yeah, STEM. I'm going to add that to physics. I forgot Najila is doing this class. Hey, Najila. I'm excited to have you here. Who else can give me something else? Anything we can add. Maybe a different type of engineer. Maybe something engineers do. Biotech. Thanks, Arn. That's a good one. I like that one. I'm going to put that one down here. Biotech. What does biotech if you're civil engineering? Thank you. Who can give me another type of engineering? Biotech, that's good. Civil is, yeah. What does this, can someone tell me what civil and chemical? Good. Who said that one? Oliver, thanks, Oliver. Who can tell me a type, what civil engineers actually do? What do they design? What do they engineer? What's their thing? Maybe buildings, roads. Yeah, you're right. Buildings, roads. Infrastructure. Yeah, thanks, Arn. Have we got all the types of engineers? Have we got any other types that you want to think about? Electrical. Yep, I'm going to add electrical. Yeah, actually, you know what? Electrical is different from electronics. I would say they're very similar, but yeah. Anything else? Aeronautical. All right, good one, Arn. Now, before you jump off though, what do aeronautical engineers, you spelled it correctly too, what do they work with? What do they make? What do they build? Air thingies, planes, yeah, planes, rockets. Yeah, it's pretty good. Someone also said submarines. Submarines, are something that engineers would build, that would definitely be something that would build. One that you guys are missing is begins with A, automotive. Thank you. You got it as I was writing it down. Elaine. Thank you, Elaine. As I said, I have to learn all your names. Like, this is going to be really hard. But automotive engineers. And what are automotive engineers? What do they make? What are they good for? Cars. Anything that sort of moves on a car is like an automotive. I'm pretty happy with that. I think we've got a lot of the big main ones. I'm usually, yeah. I'm actually going to take a quick screenshot of this guy, just so that I can refer back to it later on. But yeah, no, you guys have done pretty well. The one that there are a couple that we could talk about that you may have missed, but you know, like we are missing. Where am I? Hold on, I've just sort of lost my page. We're sort of missing environmental is one that I always like to talk about. Now, environmental, but we're not going to, unfortunately, Everest, we're not going to be learning about hydraulics. I mean, we can. The other one that I always like is mechatronics, which deals with electronics and coding, but it deals with robotics actually. But I like what I'm going to do here is I'm going to circle this section here. This in red is sort of some of the tools that engineers use. Some engineers use code, some engineers use physics force, but essentially what the big term here would be to talk about is science. For example, biotech is a type of science, but it's not physics. Nuclear engineering is definitely one that I was going to add to the list. Nuclear engineering is going to go over here. And whereas this is sort of like, and this was probably said very early on by I think Dylan and someone else I think said it, not after Dylan said it to me privately, improving life is sort of one of the main things that an engineer does. And I like that. It's sort of the main point. But let's jump from here. Let's go back to here for a sec. And if you look here, by the way, in this picture is a bunch of the main things that I took away. Engineers, we've got a biotech, we've got a planes, aeronautical, electricity, environmental. Over here, we've got, like, again, infrastructure. So this is civil engineering. But of course, this was made, you know, way in like ancient Roman times. But still, understanding water transport is still going to be part of engineering. So what do I think engineering? What do I think is engineering? What is the main parts of what makes engineering? Nanotechnology and quantum technology, that argument is an interesting one. Who said that? That was someone quite smart, someone who's got some opinions. That one is, I think it's too much science at the moment to be engineering, but I definitely don't think that quantum engineering is very far away. I reckon it's very close. So at the moment, what do I think engineering is? I like this quote. Well, this is not a quote, but this is my opinion. Engineering is using maths and science to solve problems. Now I've got a quote from Henry Petroski, who was a famous engineer. He said, science is about knowing, engineering is about doing. And especially once I got to university and I got to work with a lot of different people, including engineers, I definitely started to appreciate this sentiment a lot. Science is great. Science is, I teach science and I love teaching science. Science is all about understanding the world and trying to explain it and like discovering new parts of the world, you know, whereas engineering is not about discovery. Engineering is about solving problems. Okay, a scientist can go and discover a new mineral that's in the ground and, you know, can find out how that mineral forms, how to crush it, what type of chemicals it can be used in, what kind of structures it can be used in, how it reacts to certain things. But an engineer is the person that takes that mineral and says, hey, given that the scientist has tested it and said it's really good for building buildings, I'm going to use this to solve a problem. I'm going to build a building out of it. A person, you can have a software engineer, people that make all this, or scientists that make all this great computers and solving programs, but you need to have a software engineer come along and say, hey, I'm going to solve a problem. I'm going to create a website that's going to help me communicate. That is solving a problem. That's not necessarily using science. That's using science to solve a problem. And sometimes you might use math to solve a problem. So that's what engineering is. It's not about finding things out. It's not about knowing. It's about doing. And so that sort of like takes us to the, in my opinion, roughly the halfway point of the lesson. We're almost, by the way, at the end of period 5. So now what I'm going to talk briefly about is expectations. And then we're going to come back to engineering and what we're going to do with the subject in a little bit. But yeah, normally expectations in this section, what I would do is I would go through the basic rules of the classroom and so on and so forth. Obviously, that's going to be a bit different because there aren't many, because we're teaching remotely, it's a bit difficult to do. So I'm just going to break it down really quickly anyway, though. So the 2 rules that I have at every one of my classes is, and the rule number 1, everyone has a right to feel safe. Now, in an online environment, what does that mean? In an online environment, that means that we aren't putting each other down. We aren't saying you're an idiot. We are trying to support each other. We're trying to, you know, if someone says something wrong, you know, or something you think is stupid, you don't laugh at them, you don't call them an idiot. You just let it roll and just ignore it. And then, yeah, maybe you could be the person that helps them out. But that's how we feel safe. In a classroom environment, I would be telling you guys about, you know, throwing stuff around, blah, blah, blah. But obviously, that's not really possible. The second rule is everyone has a right to do as much work as possible. Now, what that means is that's not an expectation that you guys work in my class. I mean, that is one of the things I would expect of you guys, but the expectation is not that you would work, but everyone has a right to be able to work. So that means that you shouldn't be distracting other people, okay? If you guys are messaging each other, being like, hey, I'm distracting, then that's gonna be breaking my rules. But obviously it's gonna be a bit hard for me to enforce that. So I'm just gonna have to trust that you guys are doing the right thing. Other expectations that aren't necessarily here. The first one is that during the term, I'm going to be giving you guys homework tasks. You will normally have a week to complete that homework task. And then I'll also provide you with the answers. At the end of that week, I'm going to get you to upload those responses. You can upload them by taking a photo of it and uploading it to the classroom, or you can instead type it up into a Google Doc or something like that and share it with me. I don't really care how you get it to me, as long as you somehow send me the information that you've been working on. And as I said, the other expectation is that you give it a try. Okay, I'm not expecting you guys to be maths whizzes. I'm hoping that some of you guys are, because it is called engineering maths, so expect maths problems. But, you know, I want everyone to at least give it a try. I think they're the main, the other class rule that I have, I don't really, other teachers really care about whether or not you show your faces on the Zoom. I don't actually care if you show your faces. One thing I do want from you though, is I want to make sure that everyone's name has to match what it says in the role. The reason for that is that I need to be able to check whether or not you're here or whether you're absent. And it doesn't have to match your whole name, but it needs to like be something that I can look up. So you can't just have like, you know, Snoop Dogg or something like that. It needs to be a name that I can look up and be like, okay, this person's present. Because at the end of the lesson, sometimes what I do is I'll just be like, okay, which students said they were attending on the Google Classroom, and then who was actually in the class. So I like to compare it. And if I can't recognize you, then I'm going to be like, well, they weren't here. And you're like, oh, I was here. But I'm like, well, I didn't see it. So that's the other rule, is make sure that your name is the same. And the other reason as well is that last term I had some students come into my class that weren't enrolled in the class, and they just decided to bully this random student in my class. It's like, that's not on. It's like, I can't protect you guys if you don't use your actual name. You don't have to use your full name. You can just use your first name if you want, but I need to be able to see your name. Okay, is that cool? Questions? Pauses, waits to see if anyone says any questions in chat or out loud. Okay, let's go. Oh, okay, I'm gonna skip. Oh. You got a question, Everest? Go. That was the bell. If we come back, we'll be doing pracs or projects. Yes, we will, and that's my plan. One of my plans is, of course, we're going to be doing a bit of a robotics project. I've decided to, because and the reason we're going to do robotics is because what it will do is it'll bring in those skills in design, coding, and electronics all in one. I would really love, I'm planning on getting you guys a chance to actually get in there and work on it and build something. But if we don't come back, then I'm going to have to figure something out. The good news is that the robotics project would probably go over the term 4. So because we're in term 2, it's probably not going to happen. It's probably term 3, sorry. It might mean that we can still do the project term 4, but I'm not sure. Is there going to be an exam? Normally there is an exam for engineering maths. However, I did not do an exam last semester with my students, and my choice on whether I would rather you guys not do an exam, just because this year is whacked out enough as it is. You guys shouldn't have to do an exam, but it's not my call, it's the coordinator's call, so I'll let you know when I know about exams. Okay, as for this is the homework task. Now I've forgotten to put this on the classroom because I'm gonna give you guys another homework task, but it won't be due until a little bit later, but I'm not going to do that now. This is usually the first task that I give people. Now, I haven't actually even given you guys the list yet, so I will explain all this in a post in the thread on, I'll explain all this in a I'll explain all this in a thread later on. But at the moment, let me just talk to you about it. What I showed you guys to start with that engineer, I'm going to get you guys to make something similar for me. And what that similar thing is going to be is it's going to be this. What you're going to do is your task is to write approximately 100 words, and not very long, and a photo about a stolen idea. Now, the stolen idea, how it's going to work, don't start writing it yet, is I'm going to give you a person from a list. Okay? So the list is going to have a bunch of names on it. Let me see if I've got a copy of the list. Here it is. I'm going to give you a copy of, I'm going to give you guys a name. And on that name, here's a bunch of names here. Robert Kern, Margaret Knight, Nettie Stevens. Some of you guys, some of these guys you may see that are familiar. Some of these guys, for example, where is the most familiar one? Where is he? I'm looking for sorry, give me a sec. Edison. Thomas Edison is here somewhere. I think it's like Edison, Tesla. Here's one that's, you know, this is the one that I'm talking about. Now, what your job will be is your job will be to write about these different people and their inventions, right? But here's the catch. Their inventions were all stolen from them. So every person on that list invented something, but their invention was stolen in some way. Their idea was stolen. In some of these ideas, it was stolen by their person's husband or something. Sometimes it was stolen by a company. Sometimes it was even stolen by their teachers would steal their ideas and pass them off as their own. Sometimes it was the stealing and the person made zero money. Sometimes they won legal battles and actually got the money back. So what it's going to be, it's going to be your job to write 100 words on why that person became, like, you don't have to do all of these things, but the main one is what was their idea and why was it stolen? And so maybe you look up, and so here's an example of one from a couple of years ago. This was a student that wrote about Lise Meitner. And so she was involved in discovering nuclear fission. She worked as a chemist. When Nazi took over, she continued to secretly work with Hahn. Hahn performed the experiments for nuclear fission. Meitner backed up his experiments. Her work was stolen because when the findings were published, her name was left off the paper. So that was a pretty good one. The only part that I didn't like about Keegan's one is he didn't actually tell me, you know, why do you think it was stolen? Like, do you think, and I reckon the reason it was stolen is because this was the 1900s. Back then, women weren't really considered to be good scientists. So I reckon that the reason why it was stolen in this case was because she was a woman. And I would really love you guys to give me your opinion about why. You are going to be uploading this to the classroom. And what I might do first at the very end of the lesson is I'm going to get you guys to maybe pick a person that you guys would like to do out of the list. I think the best way to do that would be to take this list. If I go Control A, Control C, if I take this list, and I jump over here, and this is trying to do some. Oh, I don't think it's going to be able to work because I reckon that the internet's too crap. I think it's the internet's struggling as it is to bloody put up this yeah, it's not going to work. I'm going to have to do this after the class. I'll put up a place for you guys to pick which person you want to do, and then I'll give you guys instructions on what you need to write. But it only needs to be 100 words and needs to have a picture. Yeah, no, this is gonna, look at this. Look at this. It still hasn't loaded yet. Oh, this is crap. Also, by the way, I'm a bit of a nerd, and I usually upload these videos to come to YouTube afterwards, so that you guys can actually look up later on to see what you missed in case something drops out. But it probably won't do it all the time, but just be aware. No, look at that, it's taking too long. So that's the homework task. That'll be due next week. Okay. Now, sorry to do this to you guys again, but could someone tell me whether or not you can see the screen that says the homework with the green pictures with the PowerPoint slide? Just say in the chat if you wouldn't mind, just whether or not you can see it. Yep, thank you, Everest. I can't tell what's being displayed or not. So I believe the next step is to talk about the engineering process and being an engineer. Now, for this step, what I love to do what I'm going to do is I usually show students a YouTube video. Now what I'm going to do is I'm going to play the YouTube video through here. But what I'm also going to do is I'm going to quickly send you a link in chat if you want to watch it on your own screen in case it gets too laggy. So we're going to watch two videos. One video which is just basically what an engineer does, and one video which is what the engineering process is. It's the next video in the series. I'm going to warn you guys, the videos that I'm about to show you are sort of more directed towards primary school, so you're probably going to watch it and be like, oh my god, but it is still got some interesting ideas. And at the very end of it, I want to list the 7 steps that is the engineering process. And that's what I'm going to get you guys to write down in your books. This pencil here means that's what I want you to write down. 7 steps in the engineering process. So let's do we'll have to see how we go.
How can we communicate with people who live far away? These were problems that people struggled with for a long time. Until recently, before there were things like cars and phones and computers. And you know who solved those problems? Engineers. But do you know what an engineer is? The short answer is that an engineer is someone who wants to know how and why things work. Now, I want to know how and why things work. But does that make me an engineer? Not quite. Besides being naturally curious, an engineer is a person who designs and builds things, like machines or systems or structures that help solve a specific problem. There's more than just one type of engineer, too. But no matter what type of engineer someone is, they have to ask themselves 3 very important questions when they're working. Number 1, what is the problem that needs to be solved? And number 2, who has the problem that needs to be solved? And most importantly, number 3, why is this problem important to solve? Let's take a look at some examples. A really famous example of engineering is the Golden Gate Bridge in San Francisco, California. I mentioned that there are different kinds of engineers, and the civil engineer is someone who designs and constructs buildings, roads, and, bridges. For the person who designed the Golden Gate Bridge, what was the problem that they needed to solve? People couldn't travel in or out of San Francisco, which is surrounded on both sides by water, without a boat. Who had the problem? Residents of San Francisco mostly, but really anybody traveling in the area. And why was the problem important to solve? Well, you didn't want a whole bunch of San Francisco residents trapped in San Francisco forever, even if it is a super cool city. Plus, you wanted people outside of San Francisco to be able to travel to the city easily if they needed to. So the Golden Gate Bridge was engineered as a solution to this problem. In addition to civil engineers, there are also mechanical, electrical, chemical, computer, nuclear, and software engineers, and the list goes on. Let's talk about what some of the other types of engineers do. First up, electrical engineers. Electrical engineers study electricity. They design electrical systems like circuits and computer chips. Think of an electrical object that you use pretty regularly. How about your microwave? What problem was the microwave a solution to? Cold food, right? You have an electrical engineer to thank for the ability to reheat that leftover pizza you just had for lunch. But while you might not have heard of Joseph Strauss or Percy Spencer, the engineers responsible for the Golden Gate Bridge and the microwave respectively, you've probably heard of Henry Ford, as in Ford cars. Henry Ford was a mechanical engineer, or someone working in the manufacturing industry, making mechanical things like tools, engines, and machines. Machines like cars. Ford didn't invent the automobile, but his Ford Motor Company made a lot of them. His Model T car was famous for being affordable for plenty of Americans. Ford saw that lots of people who wanted to drive cars just couldn't, because they couldn't afford the pricey vehicles that were for sale. So he engineered a cheaper model as a solution to this problem. His fellow engineers started to do the same, and now, well, cars are everywhere. Henry Ford's not the only big-name engineer. A famous engineer around today is Marissa Mayer. Mayer is the president of the internet company Yahoo and is also a software engineer. Software engineers work on computers and other products that use software to write programs to make them faster and able to do more things. No matter what kind of engineer someone is, their job at its most basic level is problem solving. Each engineer just specializes in solving certain kinds of problems. While it might seem like there are too many types of engineers to keep track of, just wait 15 years, or 50, or 100, because we'll probably have a ton of different types to add to the list by then. Think about it. Over 100 years ago, we didn't have jobs in fields like aerospace engineering, where people design and construct planes and spacecraft. We didn't have planes like we do today or need spaceships, so we didn't need people to engineer them. Who knows what machines or tools or everyday objects we'll have in the year 3015? Personally, I'm hoping for underwater cities. But whatever these things are, we'll need engineers to make them. So what do you say? Who wants to be an engineer?
Okay.
I'm gonna take a wild guess and say you've probably used the phone, and I bet you've enjoyed the benefits of a little thing we call air conditioning. You know who made those things possible? Engineers. We were just talking about engineers in our last video, people who design and build things to solve problems, and there are lots of different kinds of engineers. No matter what type of engineer you want to be though, civil, mechanical, electrical, or a kind that doesn't even exist yet, there's a series of steps that all engineers follow when they're trying to solve a problem. This process is called, wait for it, the engineering process. Makes sense to me. So what sort of steps are included in the engineering process? And why do we need it? Let's go through it step by step and discover how awesome things are made. First thing you gotta do is just do it.
Ladies and gents, I've just paused it here. This is the 7 steps. I'd like you to write these down. I'm going to keep this slide, I'm going to keep this paused here for about a minute so you can, well, maybe 2 minutes, so you can write this down. After 2 minutes, I'm going to keep playing through the rest of this video. And then I might get you guys to write down in the chat what the steps are. But at the moment, this is what I want you to write down for today's lesson. The 7 steps in design, in solving a problem with engineering. Yeah. Got about a minute and a half left. Got about a minute left. Okay, that's been on for about a minute. So I'm just gonna push play or not.
Find the problem. I mean, before you can solve a problem, you have to figure out what it is, right? For example, back in the 1800s, an engineer named Alexander Graham Bell was trying to come up with a simpler, cheaper way for people to communicate. Back then, the best you could do was a telegraph, which was an old-fashioned system of sending messages over electrical wires. Bell identified his problem. Communicating with people who were far away was expensive and took a lot of time. So his invention, or solution to this problem, was something you may have heard of: the telephone. Nice. Now, once you've figured out what problem you want to tackle, you need to do your research. You can start by just making a list of questions you have and what information you need to start answering them. You can also look around and find what other things already exist that have tried to solve the same problem. Maybe they can be improved. A good example here is the man who helped us blow stuff up. The chemist and engineer Alfred Nobel invented the explosive known as dynamite. Not because he particularly enjoyed explosions, but because miners and other people who, well, needed to blow stuff up to do their jobs needed an explosive that was safer to use. So before he started on that problem, Nobel did research to see what explosives already existed, which ones worked well and which ones didn't. This takes us to step 3. Develop a solution. After your research is done, this is where you say exactly how you think you can solve the problem. And once you've thought of a good solution, you have to figure out how it'll actually work and what it will look like. So you have to design your solution. This is where you get to draw. Civil engineers always sketch out their ideas, like buildings and bridges and towers, to show what they'll look like when they're done. Gustave Eiffel designed the famous Eiffel Tower in France, and he definitely showed up on day 1 of construction knowing exactly what it was going to look like. On to step 5, build a prototype. A prototype is just a simple model that lets you test out your design. It can be as big as the real thing's going to be, or it can be a smaller version. You just need to have a prototype so you can test it. This may be the most important step in the whole process. Engineers need to test their design to see if it works like they want it to. So, say if your building's a big tower, does it stand up? Does it stay standing up? If you're designing something with moving parts, does it work the way you want? Now, take it from me, my future engineers. You might have a great idea, a really terrific solution to a really big problem. But when you get to this step, your prototype probably won't work exactly the way you want. At least, not on the first try. Most engineers test their prototypes over and over and over again. That's why a lot of time and brain power goes into the very last step: evaluating your solutions. Evaluating just means asking yourself whether things are working the way you want, or why they are, or aren't. I like to think of this step as question everything. This is when engineers review all of the facts and ask themselves questions, followed by even more questions. What worked well? Why did it work? Why didn't it work? How could it be made better? And most of the time, the answers to these questions are going to send you back several steps. Like, once you figured out why your prototype wasn't working, you'll have to design a new solution and then build it and then test it again. Sometimes engineers go through this process 4, 5, even 6 times or more. Take Willis Carrier, the inventor of modern air conditioning. He tested his prototypes for years before he figured out the design that worked the way he wanted and solved the problem he wanted to fix. Like all engineers, he failed a lot before he succeeded. And that's okay, because he learned something from every failure, which made his product even better in the end. And I, for one, am glad he kept going. So the engineering process is a series of steps that engineers, or anyone, should use when they're facing a challenge. The process is important because it allows engineers to experiment and also to fail. Both of these things give engineers a chance to go back and improve on their original idea, giving us something even better down the road. So the next time you fail at something, don't feel too bad. Think about the telephone and the air conditioner and the Eiffel Tower, and then try again.
So yeah, so the 7 steps in the engineering process, as I said, I like how she talks about them and how she discusses them. So, but can you guys tell me, what was the first one? You guys remember what that was? Can I get someone to put it either in chat or say it out loud? Up to you guys. What was the first step in the engineering process? Yeah, to find the problem. And the second one, what do we do after defining the problem? Do the research. Exactly. Research is pretty important. What's the next one after that? After we do the research, and by the way, research means everything. You might have to look up materials, might have to look up other solutions, you might have to look up if your prop solution is even possible, safety restrictions, governmental guidelines. Then you want to make a solution, you want to, develop a possible solution. So yeah, if you want to get if you want to get students to school on time, there are lots of possible solutions. And you might have done your research to already knock out some of the possible solutions. But there might be some other possible solutions you want to do. And after you've done that, you can design it. So draw it. Of course, if you're not drawing it, you can 3D model it, you can code it, you can draw a picture of it. There are lots of different ways you can design it. It doesn't have to just be pen and paper. But yeah, then after that, I think it's build a prototype. Now again, the prototype doesn't have to be a physical thing. It's usually just a test model. You might build a prototype website, which just is like a test website. Some of the links won't work. It's just designed to look good. After that, and see, oh, actually, I don't like the whole website being purple. I think the whole website should be black or whatever. Then you want to test it. So does it work as you want it to work? Does the machine actually turn? Does it actually lift things up? Does your knee replacement prototype actually make it easier for people to run? And then you want to evaluate it. How can you make it better? And this is one of the reasons why our project is going to be a robotics project. When I first started doing this topic, the very first time I got students to build, I got them to build a bridge. And I got them to then put a bunch of weight on that bridge. And it was really interesting but then the bridge, and the students learned a lot about physics and we talked a little bit about different structures and stuff, and structural engineering, but then the bridge would break. Here's my problem, right? Once the bridge broke, that was it. That was the end of the experiment. So I didn't like that because it sort of meant that students couldn't do the project. Instead, now what we do is we make a bit of a robotics project. And the advantage of the robotics project is that if the robotics project doesn't work, right? If you are making your way through the project and then you get to a point where you're like, oh, this isn't working, what you can do is you can go back and you can do another possible solution, or you could redesign your solution and see if that works, and then retest it, change your prototype, and keep coming back until eventually you will have a working prototype at the end, and that's going to be the goal. Now, last time with the project that I did with the year 10, this topic, we got to the point where I think we had almost a fully working prototype, almost. So I'm thinking about giving you guys maybe 1 week more to work on the project, and then hopefully by then you have a fully working project, fully working system. But I'll have to let you guys know. But we'll see when we get up to that. That'll be in term 4. Term 4 is also a bit crazy because it means that you guys are also going to be going into year 11, and it becomes a bit chaotic. So we'll see how we go. But in general, that's the engineering process. Now, we've got about 5 minutes. We've got about, what have we got? 10 minutes left? 12 minutes left? Let's see. what I might do, okay, I'm going to stop there, but I'm going to get up to that point. What I might do is I would like to talk to you guys about the actual next topic. Now, this is going to be our very first maths topic. We're going to break this whole elective into 3 parts. The first part is going to be talking about motion. Now, you guys just did motion in Year 10 science. So for a lot of you guys, this should be a walk in the park. If you didn't do very well though, this is your second chance. Also, we're going to be exploring things in a little bit more depth. We're going to be looking at some new ideas, some different sort of ideas when it comes to motion. So stay tuned. Then what we're going to do is we're going to do electronics. Now, electronics or electricity is something that usually gets taught in Year 9. It's supposed to get taught in Year 9, but often teachers don't get enough time to teach it properly. So that's going to be our next thing. And the final thing is going to be the project, and that's going to be at the end. And that's going to be whether or not we get enough time. We'll see how that goes. So we're going to start with motion. The first thing we're going to start with motion is vector versus scalar. Can I get you to quickly write, don't worry about this part here. Can I get you to just quickly write vector versus scalar into your books? And then we're going to start this topic today. Because I didn't have to spend 30 minutes talking to you guys about the expectations, because ultimately behavior management is pretty simple. If you guys misbehave, I just get to kick you out of the class. It's really quite easy. So vector versus scalar. We're going to discuss what is the difference. We're going to discuss what makes them different. And to do that, we're going to start with this. We're going to quickly, I guess I shouldn't talk about this, but vectors and scalar, vectors are used all the time in engineering. They're used to construct models. They're used to construct tools and equipment and materials. This is a walker. They're even used to explore things like bioengineering, got to do with like horses and stuff. So this is bioengineering, looking at the muscle structure. So that's sort of the thing that you can use to kind of to use vectors. So the real question is what is a vector? What does it mean to be a vector? What does it mean to be a scalar? Oops, that didn't work. Sorry. Okay, so, and here's an example of how vectors can actually get used to build something like a bridge or a bridge-like structure. So what is a vector? What are we talking about vectors? You guys have never seen the word vector. Well, let's start with this idea here. I have a question for you. A man ran, well, actually, you know what? Let's do this. I just want to do a whole brand new thing here. This is not something I want you to write down, but I want you to look at this. Okay. We're going to start with this design here. I have got a sheep. That's a pretty good sheep. Now this sheep is going to go on a bit of a journey to eat some food. Okay, it's going to go, we're going to say that it travels 1 kilometer straight east. Then it's going to go 1 kilometer south. And at the very end, it's going to go 1 kilometer. It's going to go 1 kilometer west. So it finishes up right here. I have a question. I would like to ask this question in the chat. My question for you is how, and this is, by the way, this is where it started and that's where it finished. How far has the sheep traveled? I'd like you to answer that for me in chat. How far has this sheep traveled? Well, which one are you going to give? So Dylan says 1 kilometer south or 3 kilometers in total. And Dylan, you would actually be, considering you're the first person to say it, and anyone else got a different idea? Anyone say no, it has to be 3 kilometers? Yeah. So you guys have nailed it on the head. I think some of you guys are coming from advanced science, so I don't need to worry about this too much. But yeah, correct. There is 2 ways you can write down how far it's traveled. You can either say it's gone 3 kilometers. That would be a distance. That's how far it's gone. Or you can refer to this idea of displacement, which means it's gone 1 kilometer south. And that's a displacement. We need to say south because if I just said, oh, it's 1 kilometer, then you might be saying, well, no, it's not, it's traveled 3. But if you say 1 kilometer south, that means, oh, well, that's how far south it is, but that's not how far it's gone in total. Or you might say 1 kilometer from where it started. So that's the same sort of thing. It's 1 kilometer away. But this one on the right needs to have something extra. That something extra is called a direction. This sheep has only traveled 3 kilometers, but it has traveled 1 kilometer south, and that's a vector. Vectors have to have a distance and a direction. So what I'm going to get you guys to do in the last 5 minutes of the class is I would like you to write this here down. This is going to be, I think this will be the last thing we do together, and then I'm going to wrap up the end of the lesson there. So quantities that have size but no direction are called scalars. Some examples are mass. Another example is distance. Can I get someone to give me another example of a scalar in the chat, please? What's another example of a scalar? I just want one more to add to our list. No, acceleration is not. Acceleration is actually a vector. Velocity is also a vector. Time, that's a good one. Time is a scalar. So is temperature. So is volts. So is current. So is why can't I think of light intensity? There you go, there's a random one. So is sound intensity. All of these are scalars. Now a vector is different. Vectors are quantities that have both size and direction. Examples are force, velocity, displacement. There should be a comma there after force. And those are all examples of vectors. So I'm going to give you guys about a minute to copy this down with those examples in there. By the way, heads up, not changing the slides yet. You've still got 30 seconds. Whenever you see a pencil in the corner of the screen, as I told you already, that means I want you to copy everything on the slide down. In that previous slide with the sheep running around in a circle, I went through that really quickly. And the reason I did that is because there's no pencil. I didn't really want you to copy down the sheep. If you did, good for you. Take more notes. Be really diligent. You know, that's how you get your A+. But if you didn't copy it down, it doesn't actually matter. It's not going to be that exact thing isn't going to be on the test. So if that's what a scalar is and that's what a vector is, how do we signify a vector? Well, what we're going to do, you know what, just for this subject, what we're going to do is when we represent a vector, we're going to usually use a bold face letter, as in a bold letter, like a bold N or a bold S, or letters with arrows over them. So I'd like you to write this one down too. This is going to be the last slide. So arrows over them would look like this, like an M with an arrow, or you might have A, B. You might also have a tilde under them, but that's very rare that you get something like this, but you might see that still anyway. I just wanted to show you all the ways you can write vectors, just in case you see them. So that's how we can name a vector. This we call this vector M, vector AB, vector S, whatever. The magnitude of a vector is the same as saying the size of a vector. And it's the length of the vector. And it's always positive, by the way. I will point that out. It's always positive. And it's usually given with these two lines here. That means the size of something. So for example, the size of -2 is 2. The size of 4 is 4. The size of -12 is 12. That's what those two lines mean. It just says the size of it. So it doesn't care if it's negative, it just cares how big it is. And the very last thing is, what is this new word, equivalent vector? An equivalent vector is like saying two vectors are equal. They are the same magnitude and they are the same direction. So that means that the same size and the same direction. Okay? Almost the end of the day here, ladies and gents. You guys have done really well. I'm going to really thank you guys for being so patient with the crappy technology today. You guys have done well. As I said, I'm going to put these slides I'm going to put the slides, like the PowerPoint presentation, I'm going to put that on the classroom as well. So, but be aware with those slides, I have a tendency to change them during the topic. So they don't always stay exactly the same. So just be aware of that. But yeah. Okay. And so if you haven't copied this down yet, make sure I'm going to put the slides on Classroom later on, so you can access it there. Tomorrow's lesson is going to be roughly the same as this. It's going to be a shorter lesson. Hopefully the internet's a bit better. I will plan to be a bit more organized. There will be an attendance question. That was the bell. Jesus. God damn, that bell's broken.